In this video, I am going to talk about the blocking and non-blocking primitives. The basic primitives are send and receive. Send has two parameters, message and a destination. Receive has two parameters, source and a buffer. The message passing primitive we are describing so far are what are called blocking primitives, sometimes called synchronous primitives. When a process calls send, it specifies a destination and a buffer to send to the destination. While the message is being sent, the sending process is blocked. That means it is suspended. The instruction following the call to send is not executed until the message has been completely sent. Similarly, a call to receive does not return control until a message has actually been received and put in the message buffer pointed by the parameter. The process remains an alternative to blocking primitives or non-blocking primitives, sometimes called asynchronous primitive. If send is non-blocking, it returns control to the caller immediately before the message is sent. Send a blocking primitive, a call to senders. When a process calls send, it specifies a destination and a buffer to send to the destination. While the message is being sent, the sending process is blocked. The instruction following the call to send is not executed until the message has been completely sent. Send blocking primitive. The advantage of this method is that the sending process can continue computing in parallel with the message transmission instead of having the central processing unit go idle. The choice between the blocking and non-blocking primitives is normally made by the system designers. Although in a few systems, both are available and users can choose their favorite mechanism. Receive blocking primitive. A call to receive does not return control until a message has actually been received and put in the message buffer pointed by the parameter. The process remains suspended in receive until a message arrives, even if it takes hours. Send non-blocking primitive. Alternative to blocking primitive. If send is non-blocking, it returns control to the caller immediately before the message is sent. Advantage of this method is sending process can continue computing in parallel with the message transmission. Instead of having the central processing unit go idle, the choice is made by the system designer. Send non-blocking primitives. The disadvantage, sender cannot modify the message buffer until the message has been sent. Sending process has no idea of when the transmission is done, so it never knows when it is safe to reuse the buffer. The solutions are to have the kernel copy of the message to an internal kernel buffer and then allow the process to continue. Advantages, from the sender's point of view, this scheme is the same as a blocking call. Of course, the message will not yet have been sent, but the sender is not hindered by this fact. The disadvantage in this method is every outgoing message has to be copied from user space to the kernel space. Non-blocking primitives. There are two possible ways are there. The first solution to have the kernel copy of the message to an internal kernel buffer and then allow the process to continue as shown in the diagram. From the sender's point of view, this method is the same as blocking call. As soon as it gets control back, it is free to reuse the buffer. Of course, the message will not have been sent, but the sender is not hindered by this fact. The disadvantage of this method is that every outgoing message has to be copied from the user space to the kernel space. With many network interfaces, the message will have to be copied to a hardware transmission buffer later anyway. So the first copy is essentially wasted. The extra copy can reduce the performance of the system considerably. Send non-blocking primitive. To interrupt the sender when the message has been sent to inform it that the buffer is once again available. Advantages, no copy is required here, which saves the time, highly efficient and allows the most parallelism. Disadvantage in this sense, the first is programs based on interrupts are difficult to write correctly, nearly impossible to debug when they are wrong. Thread of control. If only a single thread of control is available, the choices come down to number one, blocking send, number two, non-blocking send with copy, number three, non-blocking send with interrupt. Send non-blocking primitive. The difference between a synchronous primitive and an asynchronous one is whether the sender can reuse the message buffer immediately after getting control back without fear of messing up the send. When the message actually gets to the receiver is irrelevant. Receive non-blocking primitive. A non-blocking receive just tells the kernel where the buffer is and returns control almost immediately. Again here, how does the caller know when the operation is completed? The solution is to provide an explicit wait primitive that allows the receiver to block and when it wants to. Second, to provide a test primitive to allow the receiver to poll the kernel to check on the status. Receive non-blocking primitive. Just as send can be blocking or non-blocking, so can receive. A non-blocking receive just tells the kernel where the buffer is and returns the control almost immediately. Again, here, how does the caller know where the operation is completed? One way is to provide an explicit wait primitive that allows it to the receiver to block when it wants to. Alternatively, to the designer may provide a test primitive to allow the receiver to poll the kernel and to check on the status. A variant of this idea is the conditional receive, which either gets a message or signals failure. But in any event returns immediately or with some the timeout interval. Finally, here two interrupts can be used to signal the completion. For the most part, blocking version of receive is much simpler, then it is greatly preferred. Issues in this scheme is in a system in which send calls by block, if there is no reply, the sender will block forever. To prevent this situation, in some system, the caller may specify a time interval within which it expects a reply. If none arrives in that interval, the send can call terminates with an error status. Buffered versus non-buffered primitives. Buffered versus non-buffered primitive, a call received which tells the kernel of the machine on which it is running that the calling process is listening to address at the ADDR and is prepared to receive one message sent to that address. A single message buffer pointed to by M is provided to hold the incoming message. When the message comes in, the receiving kernel copies it to the buffer and unblocks the receiving process. Buffered versus unbuffered primitive. A single message buffer pointed to by M is provided to hold the incoming message. When the message comes in, the receiving kernel copies it to the buffer and blocks the receiving process. The use of an address to refer to the specific process is shown in the diagram. This scheme works fine as long as the server calls receive before the client calls send. The call to receive is the mechanism that tells the service kernel which address the server is using and where to put the incoming message. The problem arises when the send is done before the receive. How does the service kernel know which of its processes is using the address in the newly arrived message, and how does it know that where to copy the message? So, unbuffered message passing. From one user buffer to another user buffer directly, it can be sent. Program using send should avoid reusing the buffer until the message has been transmitted. For large system, a combination of unbuffered and non-blocking semantics allows almost complete overlap between the communication and the ongoing computational activity in the user program. Buffered message passing from user buffer to the kernel buffer, from the kernel on the sending computer to the kernel buffer on the receiving computer, finally from the buffer on the receiving computer to a user buffer. Buffered versus unbuffered primitive. First approach is to just discard the message, let the client timeout, and hope the server has called the receive before the client retransmits. The disadvantage of this method is easy to implement, but client to try several times before succeeding. It may give up falsely concluding that the server has crashed or that the address is invalid. If two or more clients are using the server, condition is very worse. Buffered versus unbuffered primitive continue. Second approach, to have the receiving kernel keep incoming messages around a little while. Advantage, reduces the chance that a message will have to be thrown away. Disadvantage, introduces the problem of storing and managing prematurely arriving messages. The mailbox concept. A process that is interested in receiving messages tells the kernel to create a mailbox for it and specifies an address to look for it in network packets. All incoming messages with that address are put in the mailbox. The call to receive now just removes one message from the mailbox or blocks if none is present. In this way, the kernel knows what to do with the incoming messages and has a place to put them. This technique is frequently referred to as buffered primitive. Another option is do not let your process if there is no room to store it at the destination. Reliable versus unreliable primitive. So far, when a client sends a message, the server will receive it. Message can get lost, which affects the semantics. So far, we have assumed that when a client sends a message, the server will receive it. As usual, the reality is more complicated than our abstract model. Messages can get lost, which affects the semantics of the messages passing model. Suppose that the blocking primitives are being used. When a client sends a message, it is suspended until the message has been sent. However, when it is restarted, there is no guarantee that the message has been delivered. The message might have been lost. Reliable versus unreliable primitive. Suppose that blocking primitives are being used. When a client sends a message, it is suspended until the message has been sent. No guarantee that the message has been delivered. Three different approaches to this problem are possible. Reliable versus unreliable primitive. Three different approaches to this problem. The first one is just to redefine the semantics of sent to be unreliable. The system gives no guarantee about messages being delivered. Implementing communication is entirely up to the users. The post office works this way. When you drop a letter in a letter box, the post office does its best to deliver it, but it promises nothing. The second approach is to require the kernel on the receiving machine to send an acknowledgement back to the kernel on the receiving machine. Only when this acknowledgement is received will the sending kernel free the user process. The acknowledgement goes down from the kernel to the kernel. Neither the client nor the server ever sees an acknowledgement. Just as the request from client to server acknowledged by the server's kernel, the reply from the server back to the client is acknowledged by the client's kernel. Thus, a request reply now take four messages as shown in the diagram, in the following diagram. The next approach is to take advantage of the fact that the client-server communication is structured as a request from the client to the server, followed by a reply from the server to the client. In this method, the client is blocked after sending a message. The server's the server's kernel does not send back an acknowledgement. Instead, the reply itself acts as an acknowledgement. Thus, the sender remains blocked until the reply comes in. If it takes too long, the sending kernel can resend the request to guard against the possibility of lost message. This approach is shown in the diagram as a B part, the second diagram. In the shown in the screen, it's a B right-hand side diagram is shown. Reliable versus unreliable. The summary of these operations. Unreliable saying it does not return control to the user program until the message has been sent. Reliable sender, it does not return control to the user program until an acknowledgement has been received. Receive does not return control until a message is copied to the user buffer. Implementing the client-server model. In the previous section, we have seen the four different design issues: addressing, blocking, buffering, and reliability, each with several options. The major alternatives are summarized here. For each item, we have listed three possibilities. Simple arithmetic shows that there are 3 to the power of 4 equal to 81 combinations. Not all of them are equally good. Nevertheless, just in this one area, that is my message passing, the system designers have a considerable amount of way in choosing a set of communication primitives. Another interesting issue is the underlying protocol used in client-server the communication, as shown in this diagram. 6 packet types that are commonly used to implement client-server protocols. The first one is REQ packet, used to send a request message from a client to the server. For simplicity, for the rest of this section, we can assume that the message fits into a single packet. The next one is the REP packet that carries results back from the server to the client. Then comes the ACK packet, which is used in reliable protocol to confirm the correct receipt of the previous packet. Implementing the client-server model, the situation also will arise when buffering is not used and the server is not currently blocked in a receive call. Since having the service channel, forget that the address even exists in between calls to receive can lead to problems. In some system, a server can make a call whose only function is to register a certain address with the kernel. In that way, at least the kernel can tell the difference between an address to which no one is currently listening and one that is simply wrong. It can send TA in the former case and AU in the later. Many packet sequences are possible. A few common ones are shown in the diagram. We have a request and reply with no acknowledgement. We have protocol in which each message is acknowledged individually. And we can reduce the sequence of 3 packets that is shown in the diagram also. Remote procedure call. The goal of the remote procedure call, it should appear to the programmer that a normal call is taking place. Local versus remote procedure call. When a process on machine A calls the procedure on machine B, the calling process A is suspended and execution of the called procedure takes place on B. Information can be transported from the caller to the callee in the parameters and can come back in the procedure result. No message passing or IO at all is visible to the program. This method is known as remote procedure call or often just as RPC. The goal of remote procedure call is it makes distributed computing look like centralized computing. It aims at hiding most of the intricacies of message passing and ideal for client-server application. It allows remote services to be called as procedure, transparency with regard to location, implementation, and language. Remote procedure call, it makes transparent whether the server is local or remote. It allows applications to become distributed transparently. It makes architecture of remote machine transparent. Possible issues. Calling and called procedure are on different machines. They execute in different address spaces. Parameters and results have to be passed. It can be complicated when the machines are not identical. Either or both machines can crash and each of the possible failures causes different problems. Client and server hub. The principle of remote procedure call between a client and a server program is shown on the diagram. The function of the client stub is to take its parameter, pack them into a message and send it to the server stub. While this is very straightforward, just it is a pair of stubs are used in this one. Just a client side stub looks like a local server function. Some interface like a interface as local function, bundles arguments into messages and sends to server side stub, waits for reply. Just like as in the server side stub, looks like local client function to the server, listens on a socket for message from client stub, unbundles the arguments to local variable, makes a local function call to a server, bundles result into reply message to client stub. So client stub packs the argument with the procedure name or ID. sends the message to the server, then waits for reply, unpacks the result, and returns them to the client. Receives a request message, unpacks the argument, and calls the appropriate server procedure. When it returns, packs the result and sends a reply message back to the client. Parameter passing in a remote procedure call. While this is very straightforward, it is not quite as simple as up here. In this section, we can look into some of the issues concerned with the parameter passing in the RPACing system. Packing parameters into message is called parameter marshalling. Parameter marshalling, packing parameter, one is the passing by value and passing by reference. So we may have similar problems in representation and interpretation of integers and floating point number. If machines are different, characters can be interpreted differently. Marshalling can be defined. Packing parameters is called a marshalling. Problem is different machines have different data formats. So solution is use a standard representation. Client step marshals these parameters to the runtime library for transmission. Server step unmarshals the parameter and call the server. The reply goes back by the reverse route. Conclusion is remote procedure call provides programmers with a familiar mechanism for building distributed system. Remote procedure call facility is not an universal phenomena for all types of distributed application. It does provide a valuable communication mechanism that is suitable for building a fairly large number of distributed applications.